we are going to start on the next unit, which there's a total of 8 units, and we officially finished our 4th unit, which is good because we want to be a little bit more than halfway by the end of the semester because I'm not sure the exact date of the AP test, but it's generally like in early May, and the last semester goes pretty quickly because we get back from Christmas break, and then we got January, February, and sometimes there's some snow days mixed in, and then you got spring break in March, at the end of March always, and then before you know it, it's April, and then like you take the test in early May, so like it does go really fast the second half of the year. So we'll at least get through Unit 5, which we should get through Unit 5 just fine. And then we'll have basically the last 3 units to do after Christmas break would be the goal. And Unit 5 isn't really that much new stuff. It's basically, I feel like Unit 5 is a lot of just trying to solve AP style questions. The 5th section is a little bit of new stuff, but the first few sections here are mostly just using things you already know, just kind of putting it together and solving AP style questions. And then after Unit 5, we get to Unit 6, which is a good time after the semester because Unit 6 starts with what's called differentiation or integration, which is like the opposite of derivatives. So there's kind of like three major sections in calculus. Like the first one we did was limits, so it was like all limits in the first unit or so, and then there's derivatives, and then there's anti-derivatives or integrals, what they're called, which is like sort of undoing the derivative. So if you have like multiplication, then you have division. That's a derivative. So that's where we're going after this unit. But this unit, like I said, is a lot of just like applying things that you've already learned, whether it be in calculus or pre-calculus, and just sort of solving AP style questions. So with that being said, what you're doing in this particular section is a lot of curve sketching, which can be kind of challenging. The thing is about curve sketching is there's rarely ever like an AP question where you have to sketch a curve. So it's not something that you actually have to do like the whole, you don't have to sketch a whole graph generally on AP questions. There is a chance that you could, but it's mostly, this would be like you're given a graph of this and you have to then determine properties. So we're kind of working in reverse. So for now, we're given a function and we're going to sketch this curve without the use of a calculator. Sometimes a calculator is kind of necessary, especially when you're first starting this. Calculator can be necessary, but we'll try our best without it. And here's a curve sketching recipe, if you will. This by no means is like something you have to like memorize or anything like that. It's just kind of like tips and like sort of the order if you're going to start with a graph like a function like this and sketch a graph of it, an order of things that you want to do. You basically want to figure out all we can about a function so that we can do the best educated sketch we can. So finding the domain, something you did in pre-calc down here, reducing the function if you can, vertical asymptotes and holes, x and y intercepts, the end behavior. So all of this stuff, the first 5 steps, is actually stuff you did last year in pre-calculus. I think we've done it this year as well. But all of this is just really pre-calculus and algebra 2 stuff. And then beyond that, it's just these last really 2 things, which we're going to learn. Find the integrals of increasing, decreasing, to get the extrema, and then also the concavity. So really all just pre-calculus review or algebra 2 review. And then we're going to throw into that, how can we find the Menzel masses in the shape of the curve? So let's go ahead and tackle it. And on some of these questions, they're also given the first and the second derivative as well. Makes things a little easier. All right, so starting with the first one, finding the domain. So we only want to look really at this first equation for the domain, right? To determine the domain of a rational function, which this is, we want to figure out what makes the denominator zero. Figure out what can't make it zero. Okay? So is there anything that would make that denominator zero? Right, nothing. Yeah, it is. You made the assumption that you don't want to make, right? Which is just you see the square and it's plus or minus one. Right?
Yeah.
It is a really common mistake because if you actually set it equal to zero, you'll see that it is -1. So the square root of that is nothing. So the domain then is all real numbers. Okay. Reduce it if you can. This can't be reduced in any way. That would imply like if you can factor it out and then cancel something, you would want to do so. This you can't factor it. This won't factor it. So nothing we can do to reduce it. Vertical asymptotes and holes. How do we find vertical asymptotes and holes? I'll make little notes here. So domain really is. And you probably know this one for that kind of. Generally, when you find the domain, you want to find what makes the denominator zero. The vertical asymptotes, that's also what makes the denominator zero, right? We're vertical asymptotes. So zeros denominator for a vertical asymptote. But how do we know if it's whole?
It also makes the numerator zero.
Right. So whole is zero. Both. Well, we just already determined that the domain that there was nothing that made the denominator zero, right? So that means there's going to be no vertical asymptotes because there's nothing that makes it zero. None for that. Which also means there's no holes because you can't have a hole if it's not a zero denominator. All right, x and y intercepts. So the x-intercepts, what do we do for that? So generally, if you find an intercept, you want to plug 0 in for the other variable, right? So you would plug 0 in for y, or in this case, I go back to you, but plug 0 there. Well, what's going to make this thing 0 is just going to be the 0 of the numerator. The denominator will be undefined. So the x-intercept are always zeros of the numerator. So for this one, what's our x-intercept? Yep, just 0. You could write it out if you want to, but you can clearly see 2x cubed equals 0. Obviously, 0 is 0. So x equals 0. Right. For y-intercept, that's where we are going to now actually plug 0 in for the x's. So y-intercept. Plug 0 in for all x's. So when we do that, we get on the top, this would be 0 over 0 plus 1. So it would be 0. So y-intercept is at y equals 0. Right, and 5 is the end behavior. So end behavior and horizontal asymptotes, those are kind of the same thing. If you have a horizontal asymptote, that is your end behavior. If you don't have a horizontal asymptote, then the end behavior will be like as f(x) goes to infinity, f of x goes to whatever. So anyhow, for this one, it is a fraction. So remember when you have fractions, you want to look at the highest powers to determine the vertical asymptotes, right? So this has a bigger power on top, which tells us what?
Goes to infinity.
Yeah, it's going to be infinity or negative infinity. So I'm actually going to write this one out in sort of our end behavior style, if you will, as x goes to infinity, comma, f of x goes to. So then what we want to think is we know it's going to be positive, negative, infinity. If we plug infinity in the top, it's going to be positive. If we plug infinity in the bottom, it's going to be positive, right? So positive over positive would be a positive. So it's going to be positive infinity. It's called sign analysis. We normally did that. And then we'll do the same with negative infinity. As x goes to negative infinity, f of x goes to. And so we plug in a negative infinity. The top is going to be negative, right? And the bottom is going to be positive because you're going to square it. So a negative over a positive will be a negative infinity. So this is helpful because when we're looking at the shape, it's going to tell us that whatever happens, this is going to go up to positive infinity in the positive x direction, and it's going to be going down to negative infinity in the negative x direction, right? So it's going to tell us this is what our endpoints are. All right, now we need to do some calculus. We can do some above, below. We need to find the relative max and mins, and increasing, decreasing, all that stuff. All right, and it gave us the first derivative already, so we don't actually have to calculate that. What we do need to do is figure out the critical numbers, so where that's 0 or undefined. So, critical numbers, critical values. So look at the derivative where it's 0 would be the zeros in the numerator. So that's going to be, we set this thing equal to 0. 2x squared equal to 0. So x equals 0, right? And then x squared plus 3 equal to 0. Solve that. It's already factored for us, so x equals plus or minus the square root of negative 3, which is a non-real answer. So the only critical number is x equals 0, right? Oh, sorry, we gotta check the bottom. Yeah. Okay, so then if we check the bottom, x squared plus 1 squared. You don't have to actually write this out. You can just see what the answer is going to be. Is there going to be anything that makes it 0? Take the square root, then you're going to subtract 1 and get negative 1, right? You're going to get the square root of negative 1, so that's nothing. Okay, so our only critical number is x equals 0. So then we'll want to do a little number line. And plug in a number less than 0, so like f prime of negative 1. So when we do that, negative 1 squared would be 1, so 2 times 4, so it would be 8 over, the bottom is going to be positive 2, right? Negative 1 squared, so it'll be positive over positive. So it'll be positive. And f prime of positive 1 is going to be 2 plus 4, which is 2 times 4 again, 8 positive over positive again. So this thing actually is just positive on the whole integral, which means there's no mins or maxes, right? Because it never changes signs. So none. Right. And this PI, it took me a second to figure out what that abbreviation was supposed to be. It's supposed to be points of inflection. That's not a, it's not an AP abbreviation. It's just the writer of this textbook shows that points of inflection. So let's find those. That's the zeros of the second derivative. So zeros are undefined. So let's look at this one. Same thing. F double prime of x equal to 0, and take the top equal to 0 first. So we get negative 4x equals 0, which means x equals 0. And then x squared minus 3 equals 0. This one is going to give us some real numbers. X squared equals 3, and then square root of that. So x equals plus and minus square root of 3. So we got 3 so far. We also need to check the bottom. Set this equal to 0. X squared plus 1 cubed equals 0. For that one, it's going to be nothing again because you're going to have to go to the cube, you subtract 1 and get the square root of 1. So, nothing there. So we do have 3 points of inflection. X equals 0, positive radical 3, and negative radical 3. So we can then make our little number line. Should put an order, negative radical 3, 0, positive radical 3.
Okay, we need to click on time.
Yeah, you have to look for it. Why not?
Oh, it's because it didn't specifically ask for it on the question.
Yeah. So you have
I
to.
remember graphing it.
It doesn't really tell you, I guess. Really, yeah, it doesn't really give you instructions in this. It just. But yeah, you have to graph it. Here it does say like find time cavity.
Yeah.
Yeah, I agree with that. Instructions are kind of vague. But we'll need to know what it looks like in order to sketch it. So point less than the square root of 3, I guess square root of 3 would be like negative 2, right? Because negative square root of 4 would be beyond that. So f double prime of negative 2 is the choice. So we can figure that out, the sign of it. So on the top, we'll get positive times positive, right? Over a positive. So it'll be positive. If we choose 1, f double prime of negative 1. Alright, so in here, negative 1 will give you a positive times a negative on top, right? This negative 1 squared minus 3 will be negative. So we get negative on top, and the bottom will be positive. So negative over a positive would be a negative. F double prime of positive 1 would be a negative times a negative on top. So that would be a positive overall on top, positive over a positive. So positive. And then f double prime of positive 2 will give you a negative times negative times a positive. Negative times a positive over a positive. So negative. Okay, so here's our chart. If this one hadn't been increasing the whole time, I would say try to like put these together into intervals. Yeah, but this one's increasing the whole time, so we don't really need to worry about this one because we know it's going to be increasing. All right, and let's plot the things that we have on here. So there's no holes. Let me mark those. There's no vertical asymptotes. There's no horizontal asymptotes either. The only thing we really have is these intercepts, which is the same point because x-intercept is 0 and y-intercept is 0 and square root of 4. It's increasing the whole time, so we know it's going to be traveling up. And we know it's going to sort of start down here, right? It's going down there, and it's going to end going up there. Really, we just need to mark approximately where, like, negative radical 3 is, right? So negative radical 3 is going to be somewhere between 1 and 2, right? So it doesn't have to be exact, just a sketch. Let's just say it's here. And negative radical 3 would be somewhere in there, and then positive radical 3 somewhere in there as well. But, yeah, it doesn't have to be anything specific. I'll do 3 of these. So it's going to be increasing the whole time. It's got to go through the origin, and it just has to switch concavity. So it goes from up to down to up to down. So let's just draw something that does that. So it's going to do your best. So up, and then it should sort of shifting down there, right? And again, there's not anything scientific. It's just comes up. Somewhere in there, it switches to down, goes through 0, and it shifts up again, and then it shifts back to down, like that. And it goes positive. So like up, down, up, down. I'm gonna just pull up even though you're supposed to do this without a graph, it's always good to confirm it when you can. So it's kind of zoomed in. It's even, it's honestly kind of hard to tell that it's even concave up to begin with here, isn't it? It's pretty hard to tell where it switches. It just looks like a straight line, so it's a little too hard to even tell. You can see obviously here it switches from down to up, but then it's almost impossible to tell where it switches concave down again. I don't know, maybe that doesn't actually help much. All right, so those problems are a little tend to take a while. Let's go ahead and do another one. Here, let's try number 2. And this one should have some more of these asymptotes and things like that. So I'll start with the domain. Well, just at the original function. We want to figure out if there's anything that's going to make the denominator undefined. So we should probably actually factor this first, right, if we can. What does that bottom factor into?
X minus 1,
No, sorry. Either way, it's fine. Is -1 times -1 would be +1, and then clear that even -2. All right. So then our domain, the only thing that makes the denominator 0 is 1, right? 1 and then nothing, 0. So however you want to say that, a couple ways. One would just be all reals except not 1, but it's not really the mathematic way to write it. I don't know if we've done a lot of this notation. We've done this all x's such that x cannot equal 1. Isn't that one much? You also just,
I think you showed us that once.
we could do negative infinity to 1 union 1. If you're just, well, I don't know. Both are used commonly, so just make sure you can read both. This just says the set of all x's such that x cannot equal 1. I don't know the way that's written in the answers here. At any rate, All right, next up, vertical asymptotes and holes. So we know it's undefined at 1, so really we just need to determine if that's a vertical asymptote or a hole, right? So is 1 the 0 of the numerator? Nope. So it's a vertical asymptote, right? So x equals 1 is a vertical asymptote, which means there's no holes, because there's no other options. X-intercept is the zeros of the numerator. So what's the 0 of the numerator?
Two-thirds.
All right, y-intercept. So for that, you're going to plug in 0 for all the x's. So what ends up happening, if you can actually just kind of block out all of this stuff. Just go away. Just go, right? Anything with an x is 0, so it's negative 2 over 1. So it's negative 2. For the end behavior, slash vertical asymptote, we're looking at the highest powers. The bigger powers on the bottom, which means what for vertical asymptotes? Or I'm sorry, horizontal asymptote. Yeah, the bigger powers on the bottom, when you plug in infinity, it goes to 0. So I'm just going to write horizontal asymptote y equals 0. Because that is our end behavior. We're going to approach 0 as we go positively. All right, and now we can do our mins, maxes, and concavity. So let's start with increasing, decreasing, first derivative. So we're at 0 and undefined. So top, set that equal to 0. And we'll get 1/3. Oh, sorry, yeah, 1/3. Add that over and then divide. So x equals 1/3 would be a critical number. And then on the bottom, set that equal to 0 as well. Cube root, and then add the 1 over, so x equals 1. So these are number line, 1/3 and 1. Plug in some numbers. F prime of, just say 0. Easy for the first one. So 0 would give us 1 over negative 1, right? This would be negative. And then we could do f prime of a half in the middle. This would be a little bit more challenging. So a half would give you a negative on top, because it would be negative 3 halves over plus 1. So negative over, and then a negative. This half minus 1 would be negative a half cubed, so negative. So negative over negative, which is a positive. And then we could do f prime of 2. 2 is going to give us a negative on top and a positive on the bottom. So negative over positive is negative. Okay, so now we can find the relative mins and maxes. This is decreasing to increasing. That's a min. So a min is at 1/3. This is what I was going to note on the test. So like anytime it says a point, you got to make sure you give a point. So a point is not just x equals 1/3. A point is an x and a y value. So especially for mins and maxes, because we want to know what is the min or what is the max. If you're just giving the point the x value, well, that's fine. It tells you where the x one is, but it doesn't even tell me what the min is, right? Unless we get the y coordinate. So we do need to plug that in to get the y coordinate there. And we plug it into the original f of x. So if we plug a third into there, f of a third, that's going to be 1/3 times 3 is 1 minus 2. Plug it into the bottom. You're gonna get what? 1/9 minus 2/3 plus 1. That's not the most hard thing to do here. So -1 on top. And then 1/9 minus 2/3 would be the same as 1/9 minus 6/9. So that would be -5/9 plus 1, which would be 4/9. What do you guys come up with? And then with this fraction, we can keep change flip, right? So it would be -9/4. Some of the hardest part of this is just doing something like that without a calculator. The AP test not only tests your ability to do calculus, but to do calculations in your head in a relatively short period of time. You don't have a lot of time. All right, and then relative max would be here, so that's going to be at 1/2. We need to plug that in as well. 1/2. Oh yeah, sorry, it's 1. Thank you. That was easier. So we got 1 on top. Oh yeah, that's right. So we can't have a min or max there, right? Because we're gonna get undefined. Because we're getting 0 on the bottom. So that's a good reminder that, yeah, we said it's actually undefined there, so it's gonna be max. Right. So there's none. So if you get 0 on the bottom where it's undefined, obviously you can't have undefined as a max, right? So then just make sure you go back and look. And we did say that it can't equal 1. So all right, and then last one is inflection points. So second derivative is given there. So the zeros in the second derivative, it's pretty easy. You know, 0 is a inflection point. And then the bottom, we just do 1, right? 1 and 1, we make the bottom 1. So it's 0 and 1, the inflection points. 0, 1. So let's do this number line here with this one. So f double prime of, say, -1. Be a negative on top and a positive on the bottom. Fourth power. So negative over positive is a negative. F double prime of 1/2 would give you 3 on top. So positive on over positive. Positive. And f double prime of 2. Positive over positive, right? So positive. So let's see what all we got here. If you want to combine these, you can. So like one thing you might want to do would be like, it's totally up to you if you want to take the time to do this or not. Maybe that's, you might not have time to do all this, but start from like negative infinity to your first either critical number or inflection point. So the first one we come to is 0, right? Because these are critical numbers, and here's our inflection points. The first one we come to is 0, so negative infinity to 0. On that interval, we're decreasing because it's negative. and we are concave down. So decreasing and down. Next one, we're going to take off from 0. 0 up to our next one, which is a third. So 0 to a third. We're still decreasing, because it's still negative, but we're concave up. So we switched. So decreasing and up. And then our next interval will be a third to both of these share 1. So a third to 1, we're now increasing. And we're still concave up. And then 1's our last critical or inflection point. So then 1 to infinity. We're now decreasing, so we're negative and up. So it can be helpful to write out your intervals in that way, just to put them all together, I think. And now let's go ahead and plot the things that we know here onto our graph. All right, so we have no holes. We do have a vertical asymptote at 1, so let's move that on. And we had a horizontal asymptote at 0. So and we got x and y intercepts, so let's put those dots on. X-intercept is at 2/3, so x-intercept is 2/3, so about right here. And the y-intercept will be -2. And then we also have a relative minimum at 1/3, -9/4. And there's not really a lot of space to actually do what we need to do, but at any rate. All right, so now let's try to put this together. We do know our ends need to sort of approach this way and this way, right? We gotta go towards 0. So our first interval, -infinity to 0, is decreasing and down. So I'm going to kind of start this way. So no need to approach there. Decreasing and down is going to look like this, down to 0. And then we have a minimum just past that. But we do switch to decreasing and up. So you're not really even going to be able to see it, but switches sort of a little bit up there. Up is still decreasing. All right. And then at a third, it switches to increasing and up. And we got to go through that point, right? So increasing and up. It's kind of hard to make the shape, but just do the best that you can. And then it's undefined at 1 because we got the vertical asymptote. So this will then just continue to go up. So the vertical asymptote. And then from 1 to infinity, it's decreasing and up. So the fact that it's decreasing, we know that we actually kind of got to start up here, right? It's going to be decreasing. So you might not know what part of the asymptote to start at, but you don't start down here because then we're increasing, right? The fact that it's decreasing up means we're going to start from up there and just sort of go like that too. And let me just real quick see how close we were here. So yeah, it looks pretty good. Well, yeah, right. So I'm not gonna have time to do that one. For some homework problems, try this. Um, well, look at these. It doesn't give you really the same type of problems we did for whatever reason. It doesn't give you the first and second derivative, but I think you can find it relatively easily. Number 8 is, well, this one is a radical though. I think number 6 might be the most similar. So I want to do number 6. Um, and then let's do, these are similar, but they're not rational functions. Let's see if there's another rational one. Yeah. Oh, yeah, that's all right. So let's do this. Let's do 1, 3 will be a little different, and 6. Those 3 problems.